Now that we're familiar with logarithmic properties, we can use them to solve logarithmic equations. Here's the procedure. To solve a logarithmic equation, do the following. Number 1, collect all logarithms on one side of the equation. Number 2, use logarithmic properties to condense the logarithms into a single logarithm. Number 3, convert to exponential form. This is the point where we're using inverse operations to solve the equation. Once we convert it to exponential form, the resulting equation may be linear, it may be quadratic, it may be polynomial. We can apply an appropriate method at that point to solve the resulting equation. And then number 5, check by substitution, and always remember to disregard extraneous solutions. So let's work on this procedure on example 4. Solve each equation exactly. We have log base 2 of 4x plus 1 equals 5. Our goal is to solve for x. First of all of our logarithms are already collected on one side, and it's condensed into a single logarithm. So we're going to begin with step 3, that is convert to exponential form. So we're going to take the base, raise it to the exponent on the other side of the equals, and set it equal to our argument. So this becomes 2 to the 5th power equals 4x plus 1. 2 to the 5th power is equal to 32. So we have the equation, 32 equals 4x plus 1. Now that we've converted it to exponential form, notice the resulting equation is a linear equation, and we can solve this by isolating x. So we'll subtract 1 from both sides, and then divide both sides by 4. So it looks like our solution is 31 over 4. Let's check this by substitution. We have log base 2 of 4 times 31 over 4 plus 1, and we want to find out if that's equal to 5. In the argument, the 4's cancel, and that leaves behind 31 plus 1, or log base 2 of 32, and we want to know, is that equal to 5? And yes, this is equal to 5. Notice if we convert it to exponential form, 2 to the 5th power equals 32. Another simple way to check your equation is just to use that combo math alpha math with your calculator and type in log base 2 of 4 times our answer, 31 over 4, plus 1, and the calculator also evaluates to give us 5. Let's try our next example. So we have log base 2 of x cubed minus 19 equals 3. We have a single logarithm in this equation, so we can go ahead and solve by converting to exponential form. So we have base 2 raised to the exponent 3 equals argument x cubed minus 19. 2 to the 3rd power is 2 times 2 times 2, or 8. So we have 8 equals x cubed minus 19. What's left behind is a higher degree polynomial equation, but we can solve this easily by isolating that x cubed term. So let's add 19 to both sides. That's going to give us 27 equals x cubed, and we can solve for x by taking the cube root of both sides. It's an odd root, so we don't need the plus or minus. The cube root of x cubed is x, and the cube root of 27 is 3. So taking a look at our original equation, we have log base 2 of 3 to the 3rd power minus 19, and we want to know, is that equal to 3? So 3 to the 3rd power is 27, and 27 minus 19 is 8. And do observe, if I convert that to exponential form, we have a balanced equation. And you can certainly opt into checking that with your calculator as well. I'm going to put a box around my answer over here. Okay, next we have log of x plus 6 minus log of x plus 2 equals 1. This one's a little bit different because we have more than one logarithm. So before we can convert to exponential form, we have to use our log properties to condense those two logarithms into a single logarithmic expression. So recall in the previous video, we learned that if we subtract two logarithms, we can convert this into a single logarithm by dividing the arguments. The argument that comes from the positive logarithm lands in the top, and the argument that comes from the negative logarithm lands in the bottom. And so we have log of x plus 6 over x plus 2 equals 1. Now we're ready to convert to exponential form. But to do so, we have to recognize the base of this logarithm. Remember, if the base is not written and it's an log log, we assume that it's the common base 10. So we can convert this into exponential form as 10 to the first power equals the argument x plus 6 over x plus 2. The resulting equation here is a rational equation. And we can solve this by multiplying both sides by that denominator, x plus 2. So I'm going to apply that to both sides. Notice it cancels over here on the right. So if we distribute this 10, we're going to end up with 10x plus 20 equals x plus 6. So let's subtract x from both sides to collect x's on the left. Let's subtract 20 from both sides to collect constants on the right. And we end up with 9x equals negative 14. Divide both sides by 9 to get our proposed solution, negative 14 over 9. Let's see if this one is correct with our calculator. So I'm going to look at the original equation, log of x plus 6 minus log of x plus 2, and we're going to plug in negative 14 over 9 for x, but I'm going to let my calculator do the work this time. Remember, if it's log base 10, I've got that log button ready to go on my calculator. So our solution was negative 14 over 9. You can type it in as the alpha y equals fraction or just do negative 14 divided by 9 plus 6 minus log of negative 14 over 9 plus 2. And I'm looking for an answer of 1, and we got a 1. So our answer is correct. Now on all three of those equations, when we solved them, the answer did balance the original equation. But that doesn't always happen with logarithmic equations. So be aware of this. Recall that the domain of y equals log base a of x is 0 to infinity. So remember, the graph of a logarithm, just a basic logarithm, looks something like this. And remember, on the y-axis, there was a vertical asymptote, right? So the domain is from 0 to infinity. So this interval, 0 to infinity, is placing a restriction on x. So for this reason, it is always necessary to check that proposed solutions of logarithmic equations do not result in the logarithm of a negative argument in the original equation. Remember, this argument has to attain a value between 0 and infinity. If it does create a negative argument, we just disregard the answer as an extraneous root. Now look at example C. We got a negative answer, but that negative answer didn't create a negative argument. Negative 14 over 9 plus 6 or negative 14 over 9 plus 2, those give me positive arguments. So I'm not going to throw away a negative answer. I'm going to throw away an answer that gives me a negative argument. So there's a little bit of a difference there. Let's look at example 5. First, note the domain of the variable in each logarithm, and then solve the equation exactly. And once we get an exact solution, we'll also get an approximate solution. So in the first logarithm, we have the argument x plus 2. I want to make sure that that argument is always positive, or x must be greater than negative 2. In the second logarithm, we want to make sure that argument is always positive. So solving for x, we want to make sure that x is greater than 1. With those restrictions in mind, let's go back and solve the original log equation. So the first step is to condense these into a single logarithm. Because we're adding the logarithms together, when we condense to a single logarithm, we're going to multiply the arguments. So we'll have log base 10 of x plus 2 times x minus 1 equal to 1. We can go ahead and FOIL out that argument. We'd get x squared. Outside and inside terms would combine to give us x minus 2 equals 1. Then we'll convert to exponential form. Assuming a base of 10 here, the exponential form would be base 10 exponent 1 equals x squared plus x minus 2. Now we're no longer dealing with a logarithmic equation. Now we're dealing with a quadratic equation. To solve this quadratic equation, we could either factor or do the quadratic formula, but either of those two processes require it to be equal to 0. So let's subtract 10 from both sides. That's going to give me x squared plus x minus 12. Then we can factor. So x squared plus x minus 12 equals 0. Factors as x plus 4 times x minus 3 equals 0. So we have two apparent solutions, negative 4 and positive 3. However, let's look at negative 4. If I take negative 4 and I try to plug it into this logarithm for x, that's going to give me a negative argument. In addition, if I try to plug it into this logarithm for x, that's also going to give me a negative argument. Because x equals negative 4 is not greater than 1, it's not greater than negative 2, it's going to create an extraneous solution. Now, if you're not paying attention, but you are being diligent to check it with your calculator, notice your calculator will catch it as well. So if I have log base 10 of negative 4 plus 2 plus log base 10 of negative 4 minus 1, the calculator will tell me there's a domain problem. It's not a real answer. So if you don't catch it from paying attention to the domain, at least check your work with your calculator and you can catch it that way. Now 3 is both greater than 1 and greater than negative 2, so it's a good candidate for a solution. So let's check that one with the calculator. We'd have log of 3 plus 2, log of 3 plus 2 plus log of 3 minus 1. And we're looking for an answer of 1 because that's what we had on the right side of the equation. We got it. So the only solution that we would report in this case is x equals 3. Let's try another example. We have log base 5 of x plus 2 equals 1 minus log base 5 of x minus 2. Before we can solve, we need to collect all of our logarithms together on one side. So I'm going to add this logarithm to both sides. This ends up looking like log base 5 of x plus 2 plus log base 5 of x minus 2 equals 1. We can then condense into a single log base 5 by multiplying the arguments, x plus 2 times x minus 2. Let's go ahead and FOIL the argument. Notice those are conjugates. So when we FOIL, the outside and inside terms cancel, and we just end up with x squared minus 4. All right, we're ready to convert to exponential form. So we're going to take base 5, raise it to the exponent on the other side of the equals, and then set the whole thing equal to the argument. So we have 5 to the first power equals x squared minus 4. So we're out of the problem of having a logarithmic equation. Now we have a quadratic equation, and this one will be easy to solve with the square root property. So let's add 4 to both sides of the equation. I'm going to switch it around here, and then we can solve by taking the square root of both sides. So I'm going to take the square root of the left, and don't forget that creates a positive and a negative answer. So we have positive or negative 3. Now, if I look at the original argument, this argument has to be positive, which means x has to be greater than negative 2. To satisfy this one, the argument has to be positive, which means x has to be greater than 2. So again, we've got two solutions here. One is negative 3 and the other one is 3. If we try to plug negative 3 in right here, that's going to create a negative argument. Negative 3 does not satisfy this restriction right here. So that one's going to be extraneous. The other answer 3 is greater than negative 2, it's greater than 2, so it should balance the equation. So let's check it with our calculator. So I'm going to begin by typing in the left side. That's going to be log base 5 of 3 plus 2. So that's math, alpha, math. That's how we pick up our log base 5 of 3 plus 2. That gives me a value of 1. So keep that in mind, and let's type in the right side of our equation. we had 1 minus log base 5. So math alpha math, log base 5 of 3 minus 2. And that also gives us 1. So 3 balances the equation. That's the only solution that we would include in the solution set. So collect logarithms, condense logarithms, convert to exponential form, collect, condense, convert, and then be sure to disregard extraneous roots.